Hi everybody, just enjoying this beautiful fall day outside my house. I want to check in with you. I have to take my son to the doctor, so I probably won't be in today. But I'm going to teach you via the iPad about sweat and dew point and clouds and stuff. So here we go. So we talked before about why we sweat back on Thursday. Alright, so let's do a little quick demonstration. You guys know that I like to keep up with my fitness, when I'm not in school, so I could eat more donuts and stuff. So let's give it a shot. Now, I filmed that in slow motion, so it looked like I ran really fast, but I didn't. Ah, so sweaty. Even sweatier. Whew, got a good workout in there. Now, as I was running really fast, my body temperature heated up, and in response, my body made sweat to cool me down. But as we talked about before, the sweat that comes out of your body is the same temperature as your body temperature. So how is that going to help you cool down? Well, now I'm already starting to feel cooler because my simulated sweat is now evaporating off me, but basically that evaporation process requires energy from you, all right, to evaporate. So it takes your body temperature, your body heat, and uses some of that heat to evaporate into the gas phase. And that's what you feel is a cooling process. Just like if you touch metal. Remember we were talking about the metal has the same temperature as the wood? It's wicking away heat from you. And you're feeling that process of cooling. Hold more water than cold air can. And we already know that the temperature of the air isn't directly correlated to how much water actually is in the air, only how much it can hold. I've done my best to display two different temperature airs, warm and cold, both with the same amount of water in them. Obviously, the warm air is much larger of a cup, and it can hold more water. The cold air is a smaller cup, and it can hold less water. But in this scenario, they both have the same total amount of water in them. The warm air scenario is about 50% full. Therefore, its relative humidity is 50%. If we imagine that the cold air is the same air we're talking about here, like we just dropped the temperature of the warm air to a colder temperature, we cooled it off, took away some of its heat, all of a sudden, it doesn't have as much room to hold as much water anymore. Now, the cup with the same amount of water in it, the cup shrunk, so now the cup is 80% full of water. So its relative humidity is 80%. Now again, this could be the same air, we just cooled it off. So in this scenario, if we continue to cool and cool and cool off that air, its ability to hold water is less and less and less. So as you can see here, that's our initial scenario from the previous picture, 80% relative humidity. Then we continue to cool it off, and now that same water fills up the cup 95%. And if we cool it off enough, we can get it so that the cup holds exactly the amount of water that's in it. This condition is called saturation. Saturation, like a sponge that can't hold any more water, or your backyard after a big rainstorm, the air can reach a point where it can't hold any more water. When the air can't hold any more water in the gas phase, that gaseous water turns into liquid water in the form of little droplets. A bunch of little droplets together form up what you might know as a cloud. The process of a material changing from a gas to a liquid is called Condensation.
Obviously, on condensation.
Ellen, there's moisture on the outside of my glass.
It's condensation, Johnny.
But what about the fog on the windows?
It's not fog, Johnny. It, too, is called condensation.
Condensation.
Meanwhile, back in exercise land, if I were to run in a warm and arid or warm and dry environment, our cup might look something like this, 15% full of water. When I sweat here, the air readily takes in that extra water. On the other hand, if I'm in a warm and humid environment, or a warm and wet environment, my cup is going to be pretty full of water. So when I sweat here, the air won't accept as much water as it would have if I was in the desert, and so less will evaporate. In a dry environment, more evaporation will lead to more cooling. And in our wetter environment, less evaporation will lead to less cooling. We can use this relationship of cooling to actually measure what the relative humidity, or dew point, of the air is, using our handy-dandy air humidity tool of justice, also known as the sling psychrometer of justice. The sling psychrometer has two thermometers on it that measure the outside air temperature. One of these thermometers then gets a cloth put over the bulb, and that cloth is then dipped in water. Depending on how much moisture is in the air currently, that affects directly how much of the water on that cloth can evaporate, and therefore affects how much cooling will happen on that wet thermometer. After spinning this through the air for a couple of minutes, you'll notice that the wet thermometer actually drops down the temperature that it's reading. We can then use the information from the dry bulb thermometer and the difference in temperature that it exhibits on the wet bulb thermometer. We can determine what the relative humidity of the air currently is, and we can also measure how far I would have to drop the air temperature down to reach a point of saturation. From now on, we're going to define the temperature that you have to lower the air to make it saturated as the dew point temperature, or the temperature at which dew will form. So a lot of times you'll think about at night, or in the morning after the night, you'll come out and see dew on the grass, and that's because the temperature cooled off so much that all of the water in the air couldn't be held anymore, so it formed as little water droplets. When this happens at the ground level, when it forms a cloud on the ground, we just call that fog. But there's no inherent difference between a cloud up in the sky and a cloud on the ground that we call fog. And the way that we're able to predict those two values, dew point and relative humidity, is by using the handy-dandy charts and the handy-dandy Earth Science reference table on my favorite page, 12. It's really not my favorite page, but, for today, that'll do. Let's make a scenario up here. Let's say you go outside with your sling psychrometer and you measure the dry bulb temperature, or dB in this case, to be 14 degrees Celsius. Then you measure the wet bulb temperature to be 8 degrees Celsius. The wet bulb should always be colder than the dry bulb. First, you locate your dry bulb temperature on this chart. It's in this column that says dry bulb temperature. Here I see 14 degrees for my dry bulb temperature. So in this row right here, one of these values must be the dew point temperature for the current conditions. Next, I take a look at the top of the chart. The top of the chart says difference between dry bulb and wet bulb temperatures, or wet bulb and dry bulb. So ask yourself, what is the difference? And what does the difference mean? Difference means we're going to use subtraction. So what is the difference between the dry bulb temperature and the wet bulb temperature? If you said 6 degrees Celsius, good for you. Give yourself a good old pat-a-rooney on the back. If my difference between wet bulb and dry bulb was 6 degrees Celsius, then I find 6 in that column right here, and make a line through the column as well. Wherever these two lines meet is for the current conditions will be my dew point temperature. In this scenario, the dew point temperature currently is 1 degree Celsius. That means that the current temperature out right now is 14 degrees Celsius. That's the dry bulb temperature. And based on how much water is in the air and how much water evaporated from the wet bulb, I know that I'd have to drop the temperature all the way down to 1 degree Celsius to make the dew point happen, to make a cloud here, or fog, or dew form on the grass. If you look at the bottom of the same page, page 12, you'll see another chart that looks very similar. It's the relative humidity chart. The only difference is the numbers are different, and the numbers inside the cells are going to be in percentages as opposed to degrees Celsius. Both charts function the same way though. I find my dry bulb temperature, 14 degrees, the red line, so I know my relative humidity must be one of those values. Then I take again the difference between the wet bulb and the dry bulb, and I draw a line down that column, column 6 in this case, and that leads me to see that our relative humidity in these current conditions is 41%. So the cup is 41% full of water. Thank you for watching this. There will be practice problems that are graded in OneNote in our notebook under graded assignments in that tab. Please be nice to Mrs. Criddle.
This concludes our broadcast day. Click.